So we've hit all the topics in this section that we need to hit. Alkyl halide substitution elimination. It can do SN1, SN2, E1, E2. Alcohols substitution elimination. They can do SN1, SN2, E1, and E2. Ether substitution, no elimination. They can only do SN1, SN2. Epoxide substitution only by SN2. Sulfonate esters can do SN1, SN2, E1, E2. Sulfur-containing compounds like sulfides and sulfonium salts, darn good at SN2, doing SN2 and being SN2 upon, and quaternary ammonium hydroxides, E2 and E2 only. That was a quick recap. Should I write some of it down for us to follow along? Maybe. We'll start out with alcohols. Alcohols. Well, if you have a secondary or tertiary alcohol, allylic or benzylic alcohol, those like to make carbocations. That means SN1 or E1. If you have a primary or methyl alcohols, those are not crowded substrates. Those do 2-paths more often. There are exceptions. Hold on. The bigger deal, the slightly bigger deal, the different deal, maybe let's say it that way, the different deal with alcohols and alkyl halides is it depends more on what type of reagent you do as to whether you do substitution or elimination. So let's look at reagents. If we add things like HCl with zinc, or HBr, or HI, if we add things like acids like those are acidic conditions. That means you're going to do substitution. You'll do SN1 if it's secondary, tertiary, allylic, benzylic. You'll do SN2 if it's primary or methyl with those reagents. If you add reagents like Sokol with pyridine, Pieber with pyridine, Pickel with pyridine, those are basic conditions. That changes the way things work. You do substitution via SN2 only. That says via. SN2 only. These do SN1 and SN2 depending on the substrate you've got. But Sokol, Pieber, and Pickel do substitution via SN2 only. Acidic versus basic, you change the way that thing works a bit. Sokol and Pieber and Pickel do not work on tertiary alcohols. Beware. Does not work on tertiary alcohols. We got two more things to write down here, and I'm afraid I'm not going to be able to fit them. If you add reagents like H2SO4, H3PO4, or BS3, these are often heated, but those are acidic conditions. But those acids have big, bulky conjugate bases, and those conjugate bases have distributed electrons, delocalized electrons. We're going to do elimination. Totally not legible. Elimination down there. Elimination almost always will go E1. But if it's a primary alcohol, you're not going to eliminate a methyl alcohol because you got to have two carbons to do elimination, right? Yeah. If it's a primary alcohol, it can do E2, but that's really a special case. Remember, remind yourselves, go back to that example. We did a primary alcohol via E2, but it ended up making a carbocation anyway because we were refluxing, heating for a long time in acid anyway. So, yeah, it can do E2 if you're primary, but mostly we're going to see E1 with these guys. So we'll make some space up here, I guess. Alcohols can be substituted if you add things like HCl with zinc, HBr, HI. Alcohols can be substituted with things like Sokol and pyridine, PBR and pyridine, Picol and pyridine. That's two separate acidic and basic conditions. They do slightly different mechanisms depending on acidic or basic. Alcohols can be eliminated if you add things like H2SO4, H3PO4. That's acidic conditions. They're going to do mostly E1 megacarbocation kind of thing under acidic conditions. But alcohols, if you add something like Pacol with pyridine, that's basic. And under basic conditions, we are not ever, never, ever, never, ever going to make a carbocation. Never, ever, ever. Never, 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 never. So we're going to do elimination, but E2 only. It doesn't matter if it's primary, secondary, or tertiary. If you're adding Pacol with pyridine, you are not going to make a carbocation. I think that's a pretty reasonable summary of substitution and eliminations of alcohols, but alcohols can also be oxidized. So let's swipe this slate clean and talk about alcohol oxidations. Alcohols can be substituted to make alkyl halides. Alcohols can be eliminated to make alkenes. Alcohols can be oxidized. Oxidation, let's say that. Oxidation of alcohols can make ketones, aldehydes, and carboxylic acids. Those are the three types of functional groups you could create when you... That was ugly, and I tried again, and then it all disappeared. Aldehydes. Those are the three types of functional groups you can create when you oxidize an alcohol. Okay. We need to know if our oxidizing agents are strong or weak. I really want you to give me some examples of strong and weak oxidizing agents. I'll pause for you to think of them. You should pause too for you to think of them. You got them? Y'all ready? Strong oxidizing agents, in general, are anything with chromium and acid. Some specific examples are CrO3 with acid, Na2CR2O7 with acid, H2CrO4, that is chromic acid. Na2CR2O7 could also be K2CR2O7, sodium dichromate, potassium dichromate, it doesn't matter. Chromium with acid are strong oxidizing agents. What do strong oxidizing agents do? They turn secondary alcohols into ketones. And they turn primary alcohols into carboxylic acids. You don't have room to write the whole word. They turn tertiary alcohols into nothing. No reaction with strong oxidizing agent and a tertiary alcohol. They would turn a methyl alcohol into carbon dioxide. Well, yeah, okay. Weak oxidizing agents. That's PCC. That's chromium with base. It's officially C5H5NH+. Cl, or actually you'll see it more often, CrO3Cl-. PCC, pyridinium chlorochromate. You'll also have bleach as the weak oxidizing agent. That's sodium hypochlorite and acetic acid. You'll also see the Swern oxidation as a weak oxidizing agent. That's DMSO and oxalyl chloride. Yep. What's different in strong and weak? Weak turns tertiary alcohols into nothing. There's no hydrogen there to be oxidized, no reaction. Turns secondary alcohols into ketones, just the same. Turns primary alcohols into aldehydes. It does a weak aldehydes. Turns primary alcohol into aldehydes because the weak oxidizing agent, it just does a mild oxidation, one layer of oxidation. Yeah. We covered alcohols first because they're the most complex. They have the most things that you can do. You can do substitution to make alkyl halides. You can do elimination to make alkenes. You can do oxidations to make carbonyls, and all of those are carbonyls. You can do, alcohols can act as nucleophiles to make other groups. Alcohols as nucleophiles. We saw 2 functional groups get made with alcohols as nucleophiles. We saw esters be made, as in organic esters, and we saw inorganic esters be made. In order to make an ester, the reagents were alcohol. We saw 2 ways, plus carboxylic acid, plus extra acid. Alcohol plus carboxylic acid plus extra acid made an ester. Alcohol plus acid chloride plus pyridine made an ester. And acid chloride is kind of like a carboxylic acid, but a Cl instead of an OH over there. We drew the mechanism for those reactions, but we do not have to remember that mechanism yet. We won't have to remember that mechanism until Unit 3. Those previous, I should have said so before I erased it all. All those other reactions, we do need to know the mechanism for it if we drew it. Substitutions to make alkyl halides? Yes. Substitutions, eliminations of alcohols to make alkenes? Yes. Oxidations of alcohols to make carbonyls? Yes, except we did not draw any of the chromium mechanisms. We don't have to know those. We need to know bleach and Swern. But other than that, all the chromiums, nah. We drew these, but we don't have to know them yet. Okay, now, back to where we were. We also made inorganic esters. We made sulfonate esters. We saw how phosphate esters react as well, but we didn't actually draw how a phosphate ester is made. So we did draw how a sulfonate ester is made. Sulfonate esters are alcohol plus a sulfonyl chloride. We saw tosyl and mesyl and triple chloride react to make sulfonate esters. We do need to know the mechanism of how sulfonate esters are made. That's all the reactions that we talked about with alcohol, substitution and elimination-wise. But since we're ending on sulfonate esters, I think it makes good sense to start our next thing as sulfonate esters, because those are another functional group that we need to know how a sulfonate ester reacts. It's real easy to write a summary down here. They follow the flow chart. Follow the flow chart. Yeah. What flow chart? The one for alkyl halides that says methyl SN2. Primary SN2, almost exclusively. Secondary anions, yes. Strong base, no. SN2. Secondary anions, yes. Strong base, yes. E2. Secondary anions, no. SN1 and E1. Tertiary anions, yes. E2. Anions, no. SN1, E1. That flow chart, yeah? Sulfonate esters do all the same things that alkyl halides do. The alkyl halide flow chart. Yeah. Alcohols do not follow the flow chart. Don't do that. Sulfonate esters and alkyl halides follow that flow chart. All right. We talked about alcohols and sulfonate esters. Then we moved on to ethers. Again, I say we talked about alcohols first because they do the most things. Ethers do substitution only. They do not do elimination. The only types of reagents that ethers react with are things like HCl, HBr, and HI. They're often heated at the same time as well, but that's the only thing they react with. They don't react with H2SO4 or anything of the like. Only alkyl halides. Only acid halides like those. So we said if it's methyl primary or secondary, SN2. If it's tertiary, allylic, benzylic, SN1. SN1. And I pointed out when we talked about it then, and I will point it out again now, secondary is different. Alcohols that are secondary make carbocations. Ethers that are secondary do SN2. The other thing we talked about with ethers is when you have an SN1 versus SN1 disagreement, make better carbocation. That means make benzylic over tertiary because a benzylic carbocation is more stable than a tertiary carbocation. When you have an SN1 versus SN2 disagreement, make a carbocation. That means you're going to do SN1, not SN2. When you have an SN2 disagreement, attack least crowded. As ethers. But there's a special category of ethers called epoxides. Excuse me. Epoxides. They do substitution only, but furthermore, they do SN2 only. The big deals about epoxides were if you have acidic conditions, versus non-acidic conditions. You do different things. In acidic conditions, pronate first, you get a heteroatom with a plus charge. You're worried about carbocation character. Attack most substituted side. In non-acidic conditions, basic conditions, neutral conditions, non-acidic conditions, you're worried about accessibility. Attack least substituted side. Substituted, yeah, side. So ethers do substitution only, but epoxides go even further and do SN2 only. You got to worry about inversion and all that stuff, but yeah, epoxides do SN2 only. You got to know if it's acidic conditions or not acidic conditions. One little thing that I think is worth pointing out here is that Grignard reagents. What the heck are Grignard reagents? Grignard reagents are great. Oh boy. Grignard reagents are great at attacking epoxides and busting open epoxides. Note, Grignard reagents have very distinct steps. Number one, add the Grignard, whatever that Grignard is. And number two, add acid. Lots of students see this acid and say, ooh, this is acidic conditions. No way. This Grignard is added to your epoxide first, and the Grignard itself is a crazy strong base. After the Grignard does its reaction with the epoxide, that's when the acid comes into play. The acid and epoxide are never in contact because the Grignard destroys the epoxide before the acid is ever even added to your flask. So Grignard reagents are strong bases. They are definitely non-acidic conditions. Beware, even though there's acid as the second step, it's the second step. It doesn't count. We're coming in for the home stretch. We've talked alcohols. We've talked ethers. We've talked sulfonate esters. We've talked epoxides. Up next was sulfur-containing compounds. They almost exclusively do SN2. It's hard to say that it is exclusively SN2 because they could officially do something else, but almost always sulfur-containing compounds do SN2. They're good at doing SN2 reactions, acting as a nucleophile. They're good at being SN2'd upon if you have something like a sulfonium, sulfur with a positive thing. SN2 pretty exclusively when you have a sulfur-containing thing. And the last thing we talked about was quaternary ammonium hydroxide. They did E2 and E2 only. You got Hoffman elimination. We started off with a bang that was going to seem really confusing because alcohols can do so many things. But then we hit several other functional groups that don't do lots of things. So I think it's a pretty good wrap-up. I like it.